Okay, so we are. So we are very happy to host here Hongbo Jia. He started his career in physics and then moved to computational neuroscience and eventually to actual neuroscience in doing a PhD in the lab of Arthur Conner. So this is where I met him for the first time. And he had his first also on the groundbreaking article about dendritic calcium imaging in visual cortex. So that's you probably, most of you studied that paper, and those who didn't will. Certainly should, yes. And since then, he continued his work in the Munich lab, in Arthur Conner's lab, doing, among other things, technology transfer. So he made much of the equipment that was developed there commercially available. We have now a two-photon microscope that's is basically Hongbo's development in Munich, and he's doing this in collaboration with his Chinese affiliation. Okay, the company that produces these devices is in China, and this creates a very interesting and fruitful collaboration, three-way collaboration between Germany, China, and Israel. So Hongbo is going to tell us about this.
Thank you very much, Eli. Thank you so much. Thank you for everyone coming today. Mickey for the organization. And you see. Okay, I may try to fix this microphone on me. Does it work this way? Hello? No. Yes? Oh. Okay.
Easier to build the two-photon microscope?
Yeah, easier, yes. Thank you. I put this in my pocket. Great. So, as informed by Mickey, this lecture is not supposed to be a scientific project report. It's rather basics tutorial or showing actually somewhere in between school lecture and a practical research report. So to actually fill the gap in between, to say how the machine is built, how the principle works, and how the experiment to be done. So the title is called Optical Measurement Tools for In Vivo Recording of Natural Neural Systems. Somebody studied artificial neural systems that can also be probed. There was recently one very popular paper on this bioarchive trying to dissect the microprocessor using an analogy. But we are now talking about natural neural systems, so we need to use real physical instrumentation to measure them. And with this, I would like to give these 5 contents. First, just about fluorescence. What is fluorescence? Then the simple fiber fluorometry, and then about two-photon microscopy, and some future tools that are coming. Now the first is what is fluorescence? I mean, everyone might be doing some kind of imaging. Most of them are fluorescence imaging, some not, doesn't matter, but I think fluorescence imaging is one of the most commonly used imaging method for biology. And what is that? So we know light is an electromagnetic wave. Electromagnetic wave has a broad range. All of these can be called an electromagnetic wave. And what we see by human eye, visible light, is those electromagnetic waves at wavelengths range from 400, 650, 60 something, the blue, and then to 700, 40, 70 or so. Now, fluorescence describes the emission of light from a substance being irradiated by a light of a different color. So a different color, that is important, because there are many ways of light interacting with the materials. There are some ways that the color doesn't change, and some ways the color change, and the change is typical fluorescence. A fluorescent substance is also called a fluorophore. In this picture, the blue light hits on this thing, we don't know what this thing, and then red light coming out, this is fluorescence. And this diagram you may have seen in many talks, because every fluorescence imaging or two-photon imaging speaker will try to make use of this. But this is actually a more complicated version. So I took it, inherited from a lecture series in Technical University Munich. This is not my drawing, but doesn't matter anyway. So as we know, the materials consist of molecules, atoms. Let's just say molecules. Molecules have electrons, and electrons have so-called energy state. This means that the electrons can jump on stairs. Just imagine energy states like stairs. You have many stairs, of course. The higher you go, the more energy you need. Now, while light hits the molecule, it interacts with the electron structure such that pushes this electron energy to a higher state. This is completely random, so you don't know which energy state it will hit, but there is a certain probability. So physics or mathematics tell you you can only jump to here or jump to somewhere. These are complicated rules, but it doesn't matter. When the light hits it, so the energy of the molecule, or say the energy of the electron, goes high, and this is an intermediate. This is called excited state. Now, from this state, you imagine on a high stairs. It's not very stable. You want to go down to the basement. Now, how do you go down? You go step by step down, like this. Intermediate. Now, this state is an intermediate transition that happens really very fast for a molecule. And then, at some point, you don't want to go step by step. You want to jump. To jump back to the base floor. And this jumping for the molecule will transfer the energy to a photon, to a light, and this light goes out. This is fluorescence. Now, why do people use fluorescence for biological study? Well, first of all, it provides information on the molecular environment, which means fluorescence is specific to molecule, and you can have, of course, fancy colors. Second thing, actually, most importantly for biology, you don't want to just look at the different colors. You want to understand the physiological processes underlying your biology. So all of these parameters can be sensed by fluorescence, which means these parameters affect fluorescence yield. Thus, you can use fluorescence probe to quantitatively analyze those variables in biology systems. And it's very, very sensitive. In principle, one can even do a single molecule measurement. Actually, many people are have tried to do this, and so far it's quite good. Now, we come to the point of biosensors. People here are mostly doing calcium imaging, or try to do calcium imaging, but you have to know that there are a lot more things to be interested rather than calcium. So let's say, as a biologist, you must know all of these, but I'm a physicist, so actually I don't know. For example, I don't know what is GTPs, I don't know what is kinase, but doesn't matter for me. So for me, so far I only know calcium. Okay, so then this is just to say the imaging is not just limited to calcium. There is a great array of tools and probes that are available for biologists to measure. So we are here neuroscientists. Of course, we are interested in calcium because calcium by itself is an important signaling molecule. But of course, there are other biologists who are interested in other processes. But that's not the topic of today. So now we focus on calcium fluorescence indicators. Now, calcium signal in biology, of course, a lot of these, which I really don't know, but the last one, neuronal signaling. From single spine to brain spanning networks, from millisecond to lifetime effects. This is, let's say, it is lifetime effect, of course. Everyone needs to take in a lot of calcium, and this is not only for the bone, but also for the nervous system. So this guy, Roger Chen, so he got the Nobel Prize for chemistry, but actually not for developing those calcium dyes. It's rather for fluorescence proteins. It doesn't matter. And so, but his contribution to the biology community is really to provide very efficient fluorescence probes. And these are chemically synthesized small molecules, small in the sense compared to DNA. Those are large molecules, right? So these molecules have a calcium buffer. That means they can bind to calcium, and changing electron structure based on this binding, thus changing the fluorescence yield. So which means that this molecule has different fluorescence intensity with different calcium binding state. Another type of calcium indicator, actually now becoming more and more popular because they are relatively easier to use for biologists, because that's very biology. So these are genetically encoded proteins, similar to GFPs, right? So everyone knows GFP very well. And there are many other derivatives of GFP. In addition to this, you need to bind the GFP to certain calcium sensing domain, some part, like either, for example, calmodulin. In this case, will be for GCAMP and so on. Troponin is also a class of calcium sensing proteins that is popular. Maybe nowadays GCAMP is over popular, so people have forgotten this. But in the early time, this one was better than the early generations of GCAMP. Now, calcium indicators, they work by changing the fluorescence upon binding calcium. This we know. Okay, there are different ways actually. Either with a shift in the excitation or emission, the shift of the peak. So binding the calcium will no longer be best excited with the color, but yet another color. Or with a change in the fluorescence intensity. This is very easy to understand. Or changes in FRET. This is fluorescence resonant energy transfer. Now, in the case of a fluoride, let's say, with binding calcium and unbinding calcium, the peak of absorption is different. And actually, this can provide a quantitative measurement of the absolute calcium concentration with all these formulas, which I'm going to skip because it's not so important for the topic today. And in another case, Oregon green beta 1. This is a most popular small molecule calcium dye, which shorted as OGB1. So everyone would hear OGB1 100 times. Actually, this is now also getting a bit obsolete. So there are always newer generation dyes coming out. So these dyes are very simple, straightforward. With more concentration of calcium, they got more fluorescence. And this one, maybe you will hear it from more professional lecturers talking about FRET. Let's say you have a molecule that consists of two parts, the CFP and YFP. They are relatively close. And by absorbing a photon in this part, in the CFP part, this energy is transferred to this part, the YFP part, and then emits out yellow color. Now, by binding calcium, this gets open, so that the transfer efficiency gets down. Therefore, you have less yellow coming out. And this mechanism can be used for measuring sensing calcium as well. It's actually also a very useful tool, but it requires some more difficult instrumentation. So, calcium fluorescence signaling. Now we know. Now the question is, how do we do this? I mean, practically, how to get the cells loaded with calcium indicators. Now this is mostly talking about this small molecule chemically synthesized indicators. So what people usually call bulk loading means to load a bunch of cells. A bunch can be several hundred, several thousand, quite a big volume. It's called bulk loading. This is to make use of a chemical form called AM ester. And the dye molecule is binding to the ester, and then it becomes, let's say, soluble by the lipid membrane. So it can penetrate, pass through the lipid membrane of cells. But once they are inside the cell, they got to be this ester binding be cut by esterase inside the cell. And then the remaining part becomes cell impermeable. So it cannot get out of the cell. In this way, one can load many cells at the same time by simply pressure inject the dye solution in the tissue. But sometimes people want to load only a single cell, and therefore there are different ways. By infusion from a whole cell patch pipette, which is very straightforward to understand, you stick a little patch pipette into the cell, and over time, your dye solution from the pipette would diffuse into the cell. The second way, called electroporation, this is, let's say, an alternative, because to hold this cell on the patch pipette for a long enough time is a bit challenging. So some people want to save energy by using just one shot. This I will show later. And microinjection is something that will be done typically for isolated tissues. So in the intact living tissue, either whole cell patching or electroporation are most commonly used single cell loading, and the AM ester dye is for bulk loading. So the AM ester dye, there are several protocols describing. There's a lot of literature. I don't need to describe this in detail here. Actually, just talking about some potential problems. One problem actually with this method is the leakage. That is why small molecule calcium dye cannot be used for chronic imaging. So people want to study chronic signaling, they have to really stick to fluorescence protein that stays in the cell. For these molecules, they are always gradually either pumped out or just passively by a small probability diffusing out of the cell and then got lost. Now this one is for many of you more challenging, of course. This is using whole cell patching. So let's say patch clamp by itself is already a difficult technique, which we have a master here, you see. Think it's very trivial. But in the in vivo case, it's more difficult in the sense that your pipette needs to go through the dura. And for mouse, you can actually penetrate the dura. The patch pipette will go through. In some occasions, quite often the pipette tip will get clogged a little bit, but you can apply a strong pressure to blow out. And then when approaching the cell, apply this typical protocol of creating a pit and suck back. And all these will be represented in this video. As you can see, we are applying pressure through the tip of the pipette and approach and stick in and suck back. And then after breaking into the cell, which is yet another little trick to do, the cell over some time can be loaded with calcium dye and showing dendritic processes like this. The patch pipette stay there. You see the dark ground becoming dark. It's because over time the dye in the medium dissipate. Now the other way, electroporation, is to use a very strong electrical current pulse to deliver a shot of dye instead of have a true physical seal with the cell. In this way, you can still see some dye is being puffed out from the pipette tip, but this is actually by driving with the electrical current. I just have to say that all almost, I think, all of the fluorescent dyes, they have polarity, so they are charged. They're either positive or negative. They carry some charge. Thus, they flow with the electrical current when you apply on the pipette. This electroporation experiment we are trying to establish now with the microscope system at the moment. There are still some problems to sort out, but just for people who wanted to do this will be the expected view to see. You are using the exact same microscope, seeing the exact same image online real time, that you should expect to see this type of image. The last thing what I want to mention is calcium buffering. This is something that many people may not be aware of, particularly those who have not done fluorescence imaging. Because let's think, if you do patch clamp recording, your pipette, whatever liquid you put in there, you perturb the cellular internal solution. The same idea for calcium imaging. You put some calcium indicator in the cell. This actually perturbs, or they have to interact with whatever is in the cell, calcium binding or just free calcium ions. Now there is an important factor that people need to keep in mind is the dissociation constant. This describes how much your dye binds calcium. Let's say the higher it is, that means the higher number of this, meaning the lower affinity. Actually, it's the other way around. Now you have to know that in the cell that there are a lot of calcium binding proteins, buffers, and so on, which I don't know exactly what they are, but I just have to recognize that in the cell so many things speak to calcium. But that's why calcium is important. Doesn't matter. So what matters for measurement of calcium signals in the cell, let's say you are measuring actually free calcium, those little part of free calcium ion going into the cell upon some action, either action potential or synaptic transmission. And therefore, there's a common sense that you need to invert. You think of putting more calcium dye to have brighter image, have larger signal, and that is wrong, because having more concentration of the dye or having a brighter dye, effectively actually it binds more calcium and thus allows less calcium to change. So your sensing of the calcium change, in this case, for example, you have concentration up, the affinity up, so binding more, higher concentration, the smaller amplitude of the transient. The other way, lower concentration and lower affinity would yield in a larger change of the calcium sensing. So this is a little bit contra conventional thinking. And that's just for you to keep in mind is when doing the experiment, how much dye you put into the cell matters how much signal you get. And it's not always you put more dye, you get more. You need to put a certain amount in order to be physically sensible or detectable by the instrument. All instruments have a sensitivity threshold thing, but on top of that, it's not always, it's the contrary. Then the more you put, the less sensitive it is. And the other factor is about time constant. Now many people don't care about timing because in the in vivo case, timing is very complicated. All the time something is going on, so not only your stimulation event, but still, so generally speaking, the less concentration of dye or lower affinity, then you have a faster decay of the transient to be more sensitive to repetitive events, and the other way around for higher concentration dye or higher affinity. So with this knowledge of fluorescence, we come to something called fluorometry. It's very easy to understand. Fluorescence is a physical parameter, and fluorometry is a device or method that you use to measure it. And we typically use fiber, optical fiber, to measure this. Why is that? Because fibers are flexible. They can have the animals freely moving. Now these are optical fibers. This is toy, party toy. Doesn't matter. And you come with a very basic principle of how an optical fiber works. You have light. This is law identified several hundred years ago, that when light goes through a different medium, it got reflected. And there is a total reflection in the sense that if you, let's say, the lower is water, the upper is air, when you come with an incident angle that is larger than some value, then the light got totally reflected and not going out. Because this principle you use on a glass material to have a glass core and a shell which has a different reflectivity index, then creates such a structure that the light, when you come at the incident angle, then it always gets reflected from within the structure, and then you don't lose light, but the light don't go out. So it means how much light you put here and how much you get out. Of course, there are always little loss by each reflection, but this preserves a lot of the energy. Now there are, of course, many different types of fibers. That's depending on how you structure the core and the shell. And this is called a single mode fiber or multi-mode fiber. Let's not go into details of this one. Just say if you buy a fiber for your fiber fluorometry, you buy the multi-mode fiber. Now there's one important thing of how to feed the light into the fiber, because normally the fibers that you use are relatively thin. Their core is several hundred micrometers, while regular light sources or detector sizes are several millimeter size, and you need some kind of optics to conjugate them. This typically is done by an aspheric lens that converges light onto, this is not a theoretical point, but a certain size. And then there's a certain device that does this job, so let's just call it the fiber interfaces. There are different standards of fiber interfaces that you need to know of. The ones, for example, being used here in Eli's lab, these are called SMA. Those SMA are the same as one type of electrical cables, the same diameter, same standard. There's another standard for fiber connection, which is called FCPC. So the difference is easy to remember. SMA, you need to screw it in. The FCPC, you plug it in. That's all the difference. Now, the fiber fluorometry is a method for neuroscience, let's say first developed by Helmut Adelsberger in the Cornet lab. Back to the year, the published was in 2005, but the experiment was done much earlier. So actually this happened before, this you need to keep in mind, before the optogenetics and not after. So the laser, this is light source excitation. If you remember, fluorescence excitation needs a light. This light typically is blue. And this is being modulated by an acoustic optical modulator. This changes the intensity of light, because you don't want all the time very strong light to be illuminated, you want to adjust the intensity. This is required. And being deflected by a dichroic mirror, this mirror deflects blue light and pass through emission, which is green. So blue light coming down to the collimator, which has showed you this little lens that converges light onto the optical fiber. At the other end of the fiber, you stick into the animal or the preparation. Then this fiber collects the fluorescence underneath it, and the fluorescence coming back this way through the dichroic mirror, through a filter to block out this excitation laser, and focused onto a photodetector called the avalanche photodiode. Now, in practical, how this experiment is done, you have this fiber which has a shell that is typically either plastic or rubber. And this is the outer shell, and there's yet another shell. So one needs to strip out to expose the very tip of the fiber, make it smooth, make it flat, so on, and then implant into the animal, similar to in the manner to implanting an electrode. And this is an example of showing recording of calcium traces, calcium signals from hippocampal CA1 region in the mouse that is running around this basin. It's a very simple test experiment. As you see, these experiments can be done in a quite simple way. Just stick in the fiber, glue it well, and then leave the mouse free. Of course, on the other side, you need a complicated instrumentation, but those you don't need to worry about, because we have our friends doing them. Just want to mention this picture is important because the thing with the fiber that you don't have any image. This was just one point. If you want to be sure where you are actually looking at, typically after the experiment, one need to cut the mouse head off, slice it, and then try to retrieve the slice containing the staining region just to identify which part of the brain you are actually recording from. Then actually, of course, in the same time comes optogenetics. The optogenetics become more popular maybe from year 2007 and so on. Actually, interestingly, you find out is using the same tools. So you have a fiber delivering light. This light, blue light, also blue light, right? Hits on the cells. Cells are expressed with channel rhodopsin or whatever other compound that sends light and activate the ion channel or open receptors and so on, change the neuronal's excitability. And these things, when you come back to the same experimental scheme, the exactly the same device does the job. So this laser can be modulated by, remember here you have a modulator, so you can drive to, let's say, instead of using 1% for recording fluorescence, you drive it to 100%. Then this is a very strong light. So actually you can activate channel rhodopsin easily with this intensity of light. There are actually a trick. So even for tissue without any channel rhodopsin, if you give light strong enough, there will be heating effect that also will create activation. Some people did this control experiment. So therefore, you have to be in a certain energy level that is enough for opening those channel rhodopsins, but not creating just side effects by heating. Okay, so this picture gives you an impression of how much a volume the thing illumines. This bar is 200 micrometers. So the tip of the fiber is 200 micrometers. Yeah, so it's more or less comparable to a regular field of view by microscopy, two-photon or whatever in the high zoom mode. But of course, the fiber you can use a different size. You can have 1 millimeter, but 1 millimeter fiber won't easily stick into the brain. So that will be for surface fluorescence collection. You can even have 5 millimeter fiber as well. There are all sorts of fibers. Actually, one can also do this if you don't need a spatial resolution. Now, with this technique to be able to deliver a stimulating light, so this work done by Albrecht in Connor's lab, this is pure recording of spontaneous activity in the anesthetized mouse. We know that in anesthetized mouse there are spontaneously happening up and down state. Up state means activity of an ensemble of neurons, and then down state means almost silencing of the entire cortex. And then with the fiber, you see these beautiful transients come over time, once per several seconds. These correspond to the slow wave activity. Also in humans, there are similar analogies. Now, the mouse is given a visual stimulation. So the eye is being shined a light. This light doesn't shine on neurons, but on the eye. So this visual stimulation. Then this would evoke the slow wave. And then in this case, through the fiber, they deliver a short light pulse of several tens of milliseconds. This is a bit similar to electrical stimulation. If you have a cell, you shock the cell with the same pipette, and then of course you get a stimulation artifact which is being cut out here, but you get the response after it. So in the electrical case, you can record the current after stimulation. In this case, you can record the calcium fluorescence from the population after you activate this same set. And there are some quantifications that we don't need to worry about. So then we come to, let's say, two-photon fluorescence microscopy, basic. Why basic? Because there is, of course, advanced. So let's start from a basic microscopy, because maybe you have heard this in lecture many times. So I didn't invent this lecture myself. I collected materials, teaching materials, and put them in a way to help you understand two-photon microscopy. So this, most of that is collected from this lecture by Olympus. Olympus does quite well in this basic teaching, I would say. And we know human eye is actually an optical system. It has lenses, right? It is a lens, called a lens. Now, what human eye effectively does is to convert an object onto the retina, and then the retina sensing light, so then the brain can sense the object or the image. Now, let's say natural eye, not necessarily human eye, but many animals' eye have this focusing mechanism that will change the shape of this lens, such that when the object has a different distance, you're further away or closer, can form an image. But you see, the closer it is, the larger you see. That is a very basic concept. Now you want to see something that is very small, so small that you can't easily see by eye, even you put it so close to the eye, so you need some extra optics. And then you put a magnifying lens, like old people reading, we can have this thing, then the object becomes larger, virtually, for the eye. Then comes real microscope, or say compound microscope. There are a lot of lenses in between. All these lenses together makes, for the eye, seeing this little tiny small thing virtually appearing at 250 millimeter, which is a nominal, the best visible distance for eye, a big image. Now, what people use nowadays mostly for biology study is something called infinity corrected microscope. And why is that? You can just think, let's say we go back to the previous picture, you have this one which fixed this 250 millimeter. Your image has to appear here. But in reality, you want a more complicated microscope because you want to, say, do a lot of things. So this distance must not be fixed, and there's a way to have a set of lenses such that you form a virtual image plane at a given distance, but in between this virtual image plane and the specimen, the distance can be in theory infinite. In theory, in practice, of course, there's a certain limitation, but this is how this thing called infinity corrected. Now this makes you a great favor because you can put in here what's so-called infinity space that can be longer or shorter, then you add many things in between here. Here comes actually a lot of the modern microscope tools for fluorescence imaging, confocal imaging, two-photon imaging. All of these are making best use of this so-called infinity correction principle, that you can add a lot of parts in between. There comes an important concept, is the microscope objective. Okay, we know the objective because we buy them. They are made primarily by 4 big companies, Olympus, Nikon, Zeiss, Leica. So these names are known by almost every biologist. And of course, this tutorial is given by Olympus, so it shows an Olympus example. What is important for you is to read the numbers on this one, to be able to understand what objective it is and what does it do, whether it's good for your experiment or not. And let me explain you, not all of these are so critical or important for let's say physiological experiment. Now, first thing, screw thread. This determines whether you can put the objective on your microscope or not. And there are typically 2 standards in the old time. The one is called RMS. Some royal, the British Royal Society determined this, because this is from the Newton heritage and so on, and that has a given standard. And the other one is more metric. It's called M25. That is typically used by Nikon and Zeiss. So Olympus and Leica use RMS thread. They are usually this size, but now it's very different because each company makes new objectives. Some of them are really big. They have really big threads. So that there are a lot of non-standard threads coming out. But just to keep in mind that this is not universal. So you need certain adapters to be able to mount it on the microscope. Then the second important thing is magnification. This magnification is only meaningful if you put this objective in the infinity corrected microscope. If you put it in a different design microscope, it can be different. So you get a different size image. Just keeping that in mind. This number, oil immersion or water immersion. If here says oil, then it's oil. Sometimes water is short for just a W, and then it's water. So that's the important thing you need to know. And the other is air. So when it doesn't say anything, it can be just air, or there are other labels. So that's important to know, because for physiological measurements or imaging, you need to have a solution or some liquid medium in between this objective lens and your biological tissue. So you need to use water immersion objective. In some case, for just looking at the surface of the brain or surface of something, you use air. And the oil is typically used for fixed slices, so for higher resolution imaging of really tightly fixed tissue. The next important number to know is this called NA. Short for NA doesn't mean not available, it means a numerical aperture. Well, but it doesn't write NA on this one, so you watch carefully. This is a kind of a slash. So right after the magnification, there is this dividing thing and then the number. This number, 1.35 in here, is the NA of this objective. It's quite high in the sense that typically you don't go beyond 1.4 or 1.5 something. What does it mean? So there are, of course, there's a basic theory behind it, but I don't need to explain here because I think you must have heard it many times, this equation. Just to have the concept that in principle, the larger number this is, the higher spatial resolution you can get in theory, or the more light you can collect from the specimen. That is just the relation. Then the other things like corrected system, aperture adjustment, magnification, color band, cover glassing, these are typically important for this type of oil immersion objectives that use for really high resolution observation of fixed tissues. And for physiological measurement, they are not so critical. And water immersion objectives usually have a different design. Now, the last thing, which is very, very important, is this working distance. Means how much distance between the tip of the objective to your specimen. In let's say this distance determines how flexible you are during the experiment. Typically, for pure imaging studies, you have an objective that has 2 millimeter working distance. It's enough for looking at the let's say just exposed mouse brain. And if you want to do some fancy things like patch clamp under two-photon microscopy, then you need to stick the pipette somehow underneath like this. Then there needs really certain space that the pipette can go underneath the objective, because the pipette cannot go flat. If you go flat, then you won't be able to reach anything deep. It has to come with an angle, and this angle usually it's 40 degrees or something between 35 and 40 degrees. Therefore, the distance underneath the objective that is freely accessible, 2 millimeters is really kind of very difficult to operate. So in our case, in this setup here, we use an objective that has working distance of 3.5 millimeter, or 3 millimeter is also good enough. But 2 millimeter is really, for experience, based on experience, this is really quite short. Okay, so we spend a lot of time on objectives, but that's one of the most important things in the microscope. As you can see, we can build microscopes by putting things together, but this objective is something that last 100 years tradition is really not easy to create by your own, to really get to the theoretically possible optical quality. Now, we come to the point then, two-photon microscopy. So from that basic microscopy, we're going to do something that is two-photon. And what is two-photon? Before that, we need to know what kind of biological samples we are dealing with. Those brain tissues, typically, they are highly scattering. Scattering means that the light don't go straight, very usually. They will hit some molecule and change the direction. There is a number which characterize, let's call it scattering length. This, let's say, typically tells you how much distance does the light travels typically before hitting something and changes direction. And this is dependent on the wavelength of the light. The longer it is, the longer distance it can travel before having a high probability of hitting something. Now, we are doing two-photon microscopy. That is typically used for deep tissue imaging. Deep in the sense comparing to fixed lights that are just a dozen of micrometers thick. We are in an intact living brain. In theory, we want to go several millimeter or even several centimeter deep into the brain. We are looking at a small mouse, but some people want to look at big monkeys. But of course, so far there is not really a way to go that deep. Let's say just several hundred micrometers for us is good enough, because for this in the mouse we could see more or less through the cortex. Now, so the two-photon imaging is generally a very, let's say, almost exclusive tool for imaging beyond several hundred micrometer in the intact living brain at the moment. And why is that? And there's a history, of course. This lady, Maria Gopper-Meyer, back to the year 1930s, brought up a theory that two photons, not microscopy, because there were microscope at the time, but no one would use microscope for looking at biological samples in a living animal at that time. So this was only pure physics. Pure physics in the sense that two photons being absorbed by one molecule. And only absorption, doesn't say anything afterwards. Then in the year 1990, these two gentlemen, actually there's a third guy, but the third guy somehow faded out in history, mysteriously. So this is Webb, this is Denk. And they reactivated this old theory and added the fluorescence part. So they use this principle to hit a fluorophore by two photons. And they will show you how to get two photons out of there. And then they got some images. Those are the very early two-photon images. If you compare to what you get now, of course, now you get a much better one. But this is just history. So let's say, how do you get two photons? Very easy. Instead of one, you bring two. But how do you bring two? If you remember that diagram, this is very complicated with many stairs. Let's say this is simplified. Let's say the base stair and several of these higher stairs. This light, the blue light actually has a quite high energy per one photon, each photon, and this photon will hit the cell, hit the molecule. The molecule's electron jump to excited state, higher energy. And after a little relaxation, sets up down and then decide to jump and then emit a green. Why it emits green? Because there's already a difference in energy. As you see, the blue light hits this much from the basement to this height, but the electrons by itself come down to some random stair in between. So there's already some energy is gone. So by jumping back, you have a bit less energy than this green color. Now, to reproduce this process by using two photons. They're very easy. Then come two photons, but in red color, because each of these photons need to have less energy than this one. You can, in principle, have exactly the same, but in practical, maybe never exactly the same. Just to say the two sum up together will be enough to bring the electron to the excited state. And then the emission process is the same, because that's nothing to do with your incoming light. That's the excitation. Once it's done, it's only the molecule itself determining how much light is going to get out. So in practice, if you want to do real two-photon excitation, there needs some physical confinements, and I will explain you why. So typically, you need a focus. So they say in this very narrow point, a lot of light is being concentrated, and that's not good enough. It needs also to be temporarily concentrated. So the light coming in this wave, this wave, this wave, and not continuously shining. And why is that? So let's think you are laying in the sun. So the probability that one of your body's molecule get one photon excitation is happening about once per second. But to get two photons hitting at the same time, this is not very physical. Let's say less than 10 power minus 15 seconds.
within this time, two photons hit exactly on the same molecule. The probability it happens in the sunlight will need 10 million years. And of course, this is not a naturally happening process. So there you need some really very strong artificial condition. And that comes with the previous slide. You need something that is focused, and something that special comes in short pulses. And this picture we can skip. It's a very complicated formula. Many people don't use it anymore. People just use experience. We just need to know which things are important. So this is important thing. As explained, the continuous wave laser, which means like imagine a gun, a machine gun that is shooting bullets constantly out of the time. A pulse laser, not a machine gun, but like a shotgun that in one shot it gives out a lot of small bullets at the same time. Yeah? There are engineering-wise, of course, ways of creating lasers that does like so, repeating in 80 megahertz, which means 80 million pulses per second, and each pulse lasts it's not written here, several hundred femtoseconds. Okay. Then if you draw on the diagram, the power, the instantaneous power over time in the continuous wave laser, it's just a small value over time. In this pulse manner, then it's really in a short time, very high. It can be as high as 100 kilowatts. Then, let's say, why it makes difference? Why would you need a pulse laser? So after a lot of calculation, you ended up that in this very short time, 100 femtosecond, the instantaneous power is so high. It is so high that it's several orders of magnitude higher than regular illumination. Let's say you can imagine 10 power 5, this number of sunshine, but at a very short time on you. And of course, this will create a lot of two-photon effect. And this two-photon effect happening because of the confinement. First, you need to be confined in space, then in time. Effectively, now you have a laser source that already confines the time, so you will see then obviously the excitation happens in a very confined space. This is the point where the two-photon exciting event happening, and this long tube is somewhere in this medium, the one photon exciting happening. This is called excitation cone. This is also a typical picture you see on many lectures about two-photon microscopy, so I don't need to explain more. Now comes to the advanced part. The advanced part, first step is to how to build one. If you can build one, you are really advanced two-photon microscopist. So let's dissect this first. If you want to build one, first you need to get the parts. Let's say one microscope, you can think it's a microscope put on a table. So you can first decompose it into two parts. So which means you buy a table and buy a microscope that is already done. But maybe that's not good enough, so maybe one wants to really break it into smaller parts. So let's break it into more smaller parts. This means you have two-photon excitation. It's an ultra-fast pulsing laser, so laser, one part out. Then the excitation power adjustment. This is important because one wants to be able to adjust the power to the brightness of the image. Need some modulator. Then the light has to go through the system and somewhere hit the specimen, so you need some kind of relay path. One important thing is to create an image. So this I have not mentioned before, because you were all the time seeing that the two-photon thing happens on a point, and that point is not the image. So how do you create an image? Let's say this is a point. You see my pointer. If I sweep this pointer through a given size of field, then let's say for a computer screen you make maybe this is maybe 1024 times 768, this number of little spots that you say, then you create an image. So equivalently for the two-photon imaging, you want to create an image of a digital image of a certain precision, then we need to drive this point in a certain manner repeatedly and then form up this image by collecting fluorescence signal using photo detector. And of course, under a microscope, because what you are looking at is a very small structure, this needs to be magnified optically. And at last, there is many people just think it's just software, but it's never just software. It's always a lot of electronics involved in, and we'll call the controller of this whole device. So now with this decomposition, one can think of a menu, a dinner with many courses. The first course comes the laser, because this is the most expensive part of it. And oh, sorry for the text font. It didn't show very well here. Now there are different types of lasers available. This one based on titanium sapphire. It's short for TISA. T-I-S-A. It is not very visible. I'm sorry for that. I need to change this. This is the default choice of most users, and it's produced by two companies and had been extensively used a lot of time from the very beginning of the two-photon microscopy time, and the price is not cheap. Now there comes in the recent several years so-called fiber lasers. Those are single wavelengths because that's the fiber material determines the wavelengths which the thing can emit. At the moment, there are 780 nanometer or 1030, 1050 in between this, and then 1560. These are available. Yet there is coming 920. Will come soon. So this is not yet into practice. The existing ones are on this book here, and they are less than half the price, let's say, of compared to the titanium sapphire based one. And the third one is actually a combination of the two, if you can think. So this, of course, more expensive than the two added up together. But this is brand new. The two laser companies, they started this product from maybe year 2012, 2013 or so. And this is only for rich people. Like Arthur Conrad, for example, he has two of them. And we are here not so rich, so we use, I think the pointer got out of battery. It's okay. It's okay, I can use mouse pointer too. So let's just say this titanium sapphire based laser is the default choice of most users, which we also have here. Actually, if one wants to do very economic wise, you can use one laser to supply two microscopes. That's also the configuration that's happening here, because this laser is typically strong enough to drive two. That is, you cannot imagine one engine driving two cars, but in this case, yes, one laser can drive two microscopes. Then the second course comes laser modulator, something that changes the intensity of the laser as you desire. And there are different types of devices. The simplest one is a motorized gray density filter wheel. It doesn't necessarily need to be motorized. You can, of course, manually just dial it. This is like starter's low budget choice because it's really cheap. But the drawback is very obvious. It needs a lot of response time, in the sense that you want it to change, you need to dial. So the motor needs to drive it, and of course you need a certain time to drive to the position. Then this one, pocket cell, or in many company brochure they call it the EOM, electro-optical modulator. This is a device which, let's say, using high voltage on a material that changes the material's optical refraction index. Very complicated, not a single number, but let's say a matrix or tensor field, and effectively ended up in changing the intensity of light coming through it. And this thing is good in the sense that the response time is very fast, in a nanosecond time scale, but to buy it is quite expensive. And unfortunately, there is almost exclusively just one company in America providing this. So effectively, all of the microscope makers have to use their product. The third one is using acousto-optical modulator. This is using ultrasound to create to compress the material. When the sound travels in a given crystal, then sound wave, sound wave can create pressure. So this internal tension force in this material made this material into a not a uniform one, but let's say like bars, gratings. The gratings will then, depending on the optical property, will let through a certain fraction of light. And by changing the acoustic sound in this crystal, you can change the fraction of light that comes out of it, and it's modulating the light. These are a bit cheaper than the pocket cell, but the drawback is that it actually you need to tune it to a certain wavelength, and this is rather wavelength dependent. On a tunable system, it's not really favorable. So this one is easy to implement. Light goes through and doesn't go anywhere else. You just change the intensity. Now, how to get the light into the microscope or into the optical system that you are imaging? A simple one, just to place mirrors, guide the light. This is easy. A more complicated one, which some people have seen. There's an American company called Sutter Instruments, but I think this has changed name. It's called Bruker now. So they have developed a microscope that allows also composed of mirrors, but those mirrors can move on a certain axis, and then this makes sure the light still gets to the final target, even if you are driving the entire microscope body in all three dimensions. The last one, using fiber coupling, is also a possible choice. This I will show you in the very last slide. It's limited to one wavelength. I think just keep in mind anything related to fiber for two-photon imaging. Two-photon. One-photon is not limited. For two-photon is limited to the wavelength in the sense that the fiber has to be specially made for the wavelength that you want to reduce the amount of let's say optical aberration, dispersion, all these things that you don't want to lose light. So in the two-photon case, whatever fiber used is limited to one wavelength. Now, the next one comes the scanner. Scanner is something say deflect the light. So let's say make my pointer move. Now, there are these types of devices. Most popularly or most commonly seen, there are of course more than this. Galvo scanner is a mirror that is electrically driven by an electromagnet. That is the deflection angle. Let's say the mirror's angle is proportional to the amount of current flowing through this driver. So that is very good because then you have a linear drive. You give a current. The 1 ampere is at 10 degrees, then 2 ampere is at 20 degrees. Very simple and straightforward. This is used in the early microscope systems and also a lot now actually. The advantage is that instead of driving it like sequentially like this, you could drive in any arbitrary line like so, or like zigzag, or anyway. Then comes another mirror. It's called resonant mirrors. Those are actually mirror-based. So why resonant? So you have the mirror, but you think it's not good because it doesn't drive fast enough. Why it's not fast enough? Because the mirror has a certain inertia. And mechanically, the thing that can cycle at the fastest ever speed is that it's resonant frequency. So the people who create those mirrors, they made the mirror smaller and thus it can vibrate faster and drive it with its resonating frequency. Started with 4 kilohertz and let's say maybe 5 years ago 8 kilohertz were good. Now 12 kilohertz is this new standard. And we have this 12 kilohertz resonant scanner too. So this is the case in the microsystems here. You get compared to a linear drive, let's say tenfold, typically tenfold faster. Then the next type of scanner called AOD. You would remember it as acoustic. This is a type of a scanner similar to what I said, that modulator using acoustic wave. Instead of changing the intensity that passes through it, it changes the deflection angle. right? Driving it in a different manner, let's say. This driving is inertia free, which means there's nothing mechanically moving. So this can drive very fast. Then effectively you can create an image in a faster manner. There's a Hungarian company called Femtonics. They developed this scanning system by using two LEDs for both X and Y direction, and even the third one for changing the focus in Z. Very complicated system, and let's say, well, I'm not commenting on that. It's one of the options possible. But let's say for now, most popular choice is this one. So using resonance scanners, so it's faster and has less limitations compared to this one, in the sense that, if you remember, I said these crystals are specific to wavelengths. You have to tune the system to a given wavelength. For example, one wants to just use the microscope just to study GCamp, then you are set at 960 nanometer, then it's done. If you want to set to another one, the company need to come engineer and retune everything. But in this case, when using mirror-based scanners, you can change the wavelengths as much as you want, as long as the laser provides. There comes then the microscope, let's say microscope body. So typically you have these four big companies: Olympus, Nikon, Leica, Zeiss. These two are German, these two are Japanese. But for some reason, Olympus is most popular for those DIYers of microscope, because it's highly modular. So you can really take out every part and put in anything that you like, while the other three are kind of very close. And of course, there are other companies providing this microscope body, so because microscope principle is there. And actually, for two-photon imaging, you need really not so much optical lenses in there. So we use a different one, not Olympus. Let's come to the next. The photo detector. This is actually, if you can think of, the most important thing in the microscope system. Why it's most important? Not the scanner, not the other things, because this thing provides you all the signal. You can think of compare. This is, let's say, has a comparable position to a camera in a regular imaging system. You want always to have the best camera, so you always want, in the two-photon microscope case, the best photo detector. Those in early times, these biarc based photomultiplier tube, TB short for PMT, they have quantum efficiency 20%. What does quantum efficiency mean? Means if you hit 100 photons onto the detector, it senses 20 of them. So 80% is lost, which is quite a huge loss if you can think of. And so nowadays, let's say from maybe year 2005 or so on, it's already 10 years, not new anymore, but still many old microscopes are equipped only with the old one. So the new one, with a different material, this has a quantum efficiency about 40%, let's say twice of it. It's not only this efficiency gets higher, but also let's say bandwidth. There are also other hidden factors that are better. Let's just say twice better is already a minimum estimation. Price-wise, is also twice more, of course. And this one is totally new. It's called hybrid. Hybrid in the sense that it's still a PMT, but only one level of gain, and then combined with avalanche photodiode. This one I didn't mention that because this is not used so much in two-photon microscopy, in the sense that it has a very narrow limited bandwidth, so they respond relatively slowly. You need a quite long relaxation time. So the combination of this one with the PMT which Hamamatsu creates, is to say, if you hear the word hybrid PMT or hybrid detector, it has even a slightly better quantum efficiency and very fast response time, and very expensive. But they need high voltage to drive it, 8,000 volt. If you think of it, this is if you accidentally hit the voltage, it really shock you. So let's say typically choice of most users is then the people spell it like GASP. So this word you read as GASP PMT. Then last comes the controller. So the controller is something is a combination of hardware and software. And actually, because software is the thing which comes to user interface, so this will be categorized by the software developing platform. And there will be Java, LabVIEW, MATLAB or C based. It's typically used. MATLAB is very common here, if I can remember. Many people use this for analyzing data and also for controlling some instrumentation. But for controlling instrumentation, LabVIEW has the advantage in the sense that programming is very fast and a lot of hardware interfaces are supported. Java is used for many commercial systems because that's multi-platform. So it's very, very good, let's say, largely used imaging or instrument systems that not only for a few labs but rather for the industry and so on. And then of course these using just the very basic, the very fundamental programming language is C++. This is used by major microscope manufacturers because of course you create a professional software. Now we do in LabVIEW because what we do actually is not a one version software. So effectively every microscope is different because everyone has a little bit configuration. Sometimes we improve this component and make it better, sometimes the other one better. It's like human evolution, growing. So it's all the time growing, not twice stepping the same river and so on. So we need something that is very flexible to be able to match the hardware. So some people, let's say today you want to add this stimulation to the system, tomorrow you want to add this component to a microscope, then we are able to update the software, so to say, to be able to use these instruments. And all these things put together in Munich, this was 2011, this microscope was made. By the support of workshops. The Corner Lab has workshops in the German tradition, bit more professional than here, but still not so professional. But it's good enough for making a lot of homemade parts. And then this setup here is a main microscope, only this little. All the other supporting instruments. Here is the controller. This is a manipulator, Ludwig Neumann driver, if you can recognize. Here are some pressure injection devices, heating devices, stimulators, so on. And this computer screen effectively controls everything here. And then I started to have a lab. Okay, it's a dual identity lab and company in Suzhou, and re-engineered this into this shape. Now it looks closer to a more commercial product. It's not yet there. I'm still all the time improving it. Am I using out of time? This is supposed to be, the 1 hour or 1.5 hours? Okay, we're almost done there. So how to build one? Let's say in the framework of collaboration, Israel, China, Germany, as Ali just said. So you will see how this works in the last slide. It's a really close collaboration. Now, how to build one may not be a problem for you because you can just always call us to build one for you. But you need to understand why we want to build this one. Why you want Lotus scan and not the others. Lotus scan is something short for Lotus. This one, low power temporal oversampling. A scan is scanning, imaging, whatever. Now there is an important concept: high scanning speed. What is good for? If it's just for having the image refresh faster. Or maybe it's not really necessary. For example, if you use GCAM, then 4 frames per second in principle is good enough. Then why 40 frames per second? There's one interesting video which I recorded with my wife at home. And this is a marshmallow. This is a sweet candy that's very soft. The Americans have a grilling part of it, but not like this. I have a micro grill with a candle. You can see this thing got burnt if I hold it for short while there, but if I keep on rotating it, then it just gets a bit softer. It doesn't get burned. This kind of very good illustration of why high speed is good for biological imaging, because we can watch it again. What you want is not burning the brain of an animal, right? So it burns really fast, but you want to gain the maximum signal out of it. And in the in vivo case, many people don't consciously think of it. It's actually the tissue has a very high ability of repairing itself, in the sense that any damage, if it's not beyond a certain threshold, the tissue is able to repair itself. And it's a bit similar to this. Let's say the marshmallow, you think it's not burned when I'm rolling it, so this is burned for sure. But then comes this one. You think it's not burned, but it's actually gradually becoming softer. So there's always energy being absorbed by the brain, because you are shining light on it. But somehow in the living intact animal, this holds longer. The tissue dissipates this damage or dissipates the heat. But you need to be fast at a certain, let's say, a certain speed. So the tissue is enough to handle let's say, the local heating or local damage effect before the next irradiation comes. Then this is one factor why high scanning speed is important, not just for having high speed, but of course high speed by itself has an important role. If you see this one, we will have to play the video once again. This fine signal in the 4 Hz way, I didn't record it at 4 Hz, I just downsampled by taking, not binning, but just taking 4 frames out of these 100 frames, and you ended up capturing the transient of the big one, but missed the small one. But if you do a 120 Hz recording, then the small transient can be captured. So temporal oversampling, in the sense that it captures rapidly changing weak signals. Strong signals, as strong as GCAMP, really don't need to be captured by this. Or actually, there are also weak signals can be reported by GCAMP, but people would miss it by slow samples. People don't care. And so as long as you see something with GCAMP, we're totally happy with it. That's some different story. But this has an impact on how quantitative data you want to get. And this is also important not for just experimentalists, but also for theoreticians, because I have a lot. I don't know who of you here are pure theoreticians. No one? Oh, okay. So I'm sorry, all the time is only an experiment, but I will come with one theoretical slide, just one. I made it because of you're from Isakov lab, right? Oh, no? No. Yeah. No. Sorry. Yes. I got confused. Usual names are quite similar for same like my Chinese names sound similar for you. Okay. Actually the real core, let's say, intellectual product or intellectual value of this Lotus scan system, the software, right? It's being able to do the combined measurement, patch clamp, electrophysiology, not necessarily patch clamp, it can be cell attached or field potential, whatever physiology, combined with your imaging, and in the same time. Well, this is a post-hoc composed video. Real time you will see it on the microscope. Of course, you don't need to see that here. And this shows you a hippocampal, actually hippocampal CA1 neuron. This is done by Christine Grimberger. How to image hippocampus with two-photon imaging? Very simple. Dig out the cortex above it and expose it. Then one can perform exactly the same experiment. This is for cortex. This was extracted from 2010 the Nature paper, but Christine did exactly the same thing, but in the hippocampus, even very challenging. And you could see this is the NMDA spike, which comes very very big transient come here. So coming, everything lights up with this complex spike fire. Complex spike, what can call this? Here. With a plateau potential. But there's a whole biological story behind it. I'm not going into that. Now, the yet remains challenging is to do this imaging plus electrophysiology in the awake animals. This is, I think, so far not systematically done. Some people manage to succeed in 1 or 2 trials, but if you want to do routinely, it's really difficult because the mouse by itself moves a little bit. This doesn't matter much for pure imaging because you just simply kick out the movement artifact or the time window throughout the data on the thing is really shaking. But for the electrode, this will destroy the patch cloud. So this comes my last slide for the theoreticians. Sorry, I pressed too fast. Then what we are doing with the Lotus scan, or it's not Lotus scan, two-photon imaging, in my understanding, as a physics people, is to provide a quantitative data set for theoretical modeling. And what we are able to provide is, let's say, a fraction of neuronal cell bodies, let's say output of the neuron signal in a convolved manner, or a fraction of input side for a given cell. This fraction is quite low at the moment because in this case we are maybe capturing 1% of the given brain region. There are already many people trying to enlarge this, which now can maybe be 10% or so. In this case, let's say a neuron has maybe several thousand spines. We probably in one experiment we can capture a dozen of them or maximum 100 of them. But there are also ways to increase this number. Let's say these are the directions of working. Then the important thing in my mind, so this equation which I made, it's a bit similar to the Schrödinger equation, just we don't know what is a Hamiltonian. Because let's say if we modelize sorry, this was taken from another slide which had the animations. Sorry. How about let's just drop it out? Yes, that is better. If we modelize the neural network by the nodes and the connectivity matrix, then let's say with large enough numbers, this is so much a continuum that you can represent this by a wave function, and then this is linear form equation. Let's say only my hypothesis is that it is linear over time, but we don't know this f or the Hamiltonian of this system. Therefore, one needs a lot of measurement to characterize this. So, for example, sparse coding can be characterized as a sparse density matrix. Anyone here physics, doing physics? No. Okay. Then this is far beyond the scope. Well, we skip this one. Okay, then we are at the end of the talk. Lotus scan, we're done with this one. The two-photon microscopy, it's similar like an animal or life thing as evolution. Evolution in the sense that starting from 1990, then these three people, the stricter, yes, he faded out for whatever unknown reason. I really don't know. Just he never appeared in the developing anymore. And then the Dank, so group up with these people, Karol Swoboda, David Kleinfeld, David Tank. They were in where was it? Biolab, and yeah. Then they made the first in vivo measurement using two-photon microscopy, and then Fridtjof Hemschen joined the party, and then the two become in two directions. So Hemschen and then Connert comes from the slice physiology background and let's say implemented the method, and then Swoboda in Janila Farm developed scan image. So Hemschen all the way had his own system. Connert also has a tree, and then Mike Heuser or Mickey also there, and developed this is important, shadow patching. So actually what I showed, this patching thing was not invented by me. The method itself is invented by Michael Heuser. I kind of improve it to a manner by using this fast scanning, so I really see it in real time and everything is, let's say, perfectized. Mickey, your microscope is like same as what you use in Mike's lab? Okay. The other side. Okay. Svoboda's major contribution is of course GCAM. Everyone is using this now. Tank's major contribution after this, so virtual reality. Then comes another player is Mark Schnitzer from Stanford. He started with his little mini endoscopes. These are the Hungarians, the Roja Balázs, with IOD scanning. Sorry, excuse me.
Yeah, microscopes are not two-photon.
Right, but he made two-photon versions of it. He made two-photon microendoscopes. Mark Schnitzer. Yes, they had both. It's funny. The guy invented two-photon microendoscope first, and then reverted to one-photon. Anyway, and those four people were recognized 2015 the Brain Prize. And what will be next? So we are always, as Olympus motto, want to be faster, higher, stronger. Faster means simple, faster scanning. And not simply just faster, you can be able to also record multiple region or multiple plane at the same time. Higher in this case means deeper. The higher you go makes no sense. So adaptive optics is one of the major techniques to go deeper, but this of course go as deep as still being let's say mechanically confined. So you want really deeper, the only way is to stick in the lens in an endoscope manner. But this doesn't need to be a complete system. It can be just kind of let's say adapter. You want to combine this thing to this mouse, doesn't fit together, right? But there's something that adapts between, and that's this thing. Stronger can mean many things, either larger view or super resolution, or the animals freely moving, or multicolor, multimodal. The last thing, which I personally am focused on with my Chinese team, is to go to primates. That is the unique advantage in China, that we are not so much worried about animal protesting people. But indeed, in China, there's a huge culture, huge society of primates. We are like 40,000 macaque monkeys. Altogether, not in one place, but typical one monkey base would hold, let's say, 2,000 or this scale of monkeys. How many mice you have in one lab? It cannot be more than that. Future tools. This come only 3 more slides and we're done. This is a work which I partially participated in, not as a main player. I showed to some people here. This is, let's say, an advanced version of the Mark Schnitzer's mini two-photon microscope. It's very simple, straightforward. Light comes in with a fiber. This fiber is specially made. This is the two-photon excitation laser coming. And then a little mini scanner, this one, this big, 5 millimeter size, with a 0.8 millimeter mirror. Resonance scanning. Yeah? That's the difference compared to Schnitzer. Then everything of a microscope, but very small, miniaturized. But in addition, with the translational stage to focus in Z. If you remember, almost all of this mini microscope, they cannot have a Z traveling. You put it there, stick there, and it holds. Like in the case of Inscopics, for example. But these people there, they implemented this little micromotor. And the whole assembly on the mouse head looks like this. And you have to know this is two-photon. The two-photon means that it has authentic two-photon optical sectioning. This is a single frame in the 40 frames per second. The die is loaded. Remember how the die was loaded? But this was conventional loading via patch pipette. Not patch pipette, micro injections, the AM loading. And after loading this microscope assembly, put on the head of the mouse is let free. It's running freely. Extracted signals from the cells, you can estimate the quality. This is not GCAM, this is only a calcium dye, it's called Cal 520. This is the newer, let's say, alternative than OGB. OGB is getting obsolete. If you can remember this name, ask to buy this dye. No, don't use OGB anymore. Then comes this thing. It was the unique that the student, actually I trained him because then he knows how to do electroporation. So he electroporated several cells with a pipette under a conventional two-photon microscope, big one like we have here, and then took it out, mount the two-photon, let's say, headpiece, and then let the mouse running. So you will see this picture with several cells and dendrites in this view in a freely moving mouse like this one. The last video I can play. Good. There is this mouse, and this is the image. You can, oh, something's going on. Okay, these are only primitive experiments. The trouble there is that group don't have neuroscientists. I was there as a kind of advisory, so I was part of the initiation of the project. So we wrote a grant together, a very big one, altogether like 10 million euro, that much. Yeah, and this should be made available next year, I think, commercially. Maybe this year at SFN we can announce it, but it won't be so readily usable as a commercial product because we really have to systematically test it. If you can see the Munich microscope, that was 2011, and now you are using this one. This is 2016. We have already solved a lot of problems on the way. So that's a summary slide. Then the fiber fluorimetry is the first thing which I introduced. It made the animal you can freely move, totally easy to do. Any depth, the fiber can go anywhere, but no spatial resolution. The second thing is Mark Schnitzer's single photon miniaturized fluorescence microscope. Animal can freely move, resolution, some compromise, and depth also. And the benchtop two-photon microscope, this is still up to now superior imaging speed, depth, resolution, everything, but cannot freely move. So we are aiming at let's say Lotoscan, the next generation version, or it will be able to just miniaturize. Actually, this works as an add-on to the existing system. You are still using the same laser. That is just like I imagine is a headpiece, like the multi-channel or electrodes. You mount a headpiece on the animal and using the same exciting laser. At the moment, not exactly the same software because different developing thing, but I'm going to unify this soon. Okay, this is not scientific anymore. It's only fiction. How of you know this? Where is my Japanese friend? He left, right? Okay, okay. So you used to have a Japanese colleague here, but then you must know this. There is this neutrino detector in Japan using 11,000 photomultiplier tubes. That's why Hamamatsu is so good in making PMTs, because they had made so many of these. The Human Genome Project, of course, using PCR. What I say the next is reverse engineering of a natural brain. We need a lot of two-photon microscopes and other instruments. And with this, I would like to thank you for the patience of having really a long time. And these are the collaboration. Do you remember this person here who just left? And this is Connor. This is me. This Xiaowei is my close comrade in China. This picture, Munich lab, was taken like maybe in year 2012. I don't remember exactly. And this is my new group in China with mostly engineers and businessmen. Thank you. Okay. Yes.
What about 3D techniques like chemical lens?
3D scanning, there is now an easy way to do it. You kind of make a Z projection acquisition. So there's a possibility is you think let's think adaptive optics. You want to make the thing very finely focused, right? You do the contrary to it. Instead of focusing to one plane, you stretch it to the whole volume. Yeah, so of course you need to first